For Lab 4, titled Physics of Extreme Sports with Ropes, I examined the motion of a mass oscillating vertically on a spring and swinging in an arc. The fundamental principles relevant to this model are Newton's second law and the energy principle. Newton's second law was used to predict new velocities of the spring and mass. The energy principle states that the changes in energy delta E of a system are equal to the net work done on the object. Also, in the case of a multiparticle system, changes in the kinetic energy of a system must be accompanied by equal and opposite changes in potential energy. Thus, the change in total energy of the system equals the sum of changes in kinetic energy and gravitational and spring potential energies. It was found that the spring mass system does actually satisfy the energy principle, and the disparities between the predicted and observed motion of the system were due to drag and dissipative forces. Nevertheless, the predicted motion of the system agreed very similarly to the observed motion as represented in the system involved represents a multiparticle system in which the change in energy delta E is equal to the sum of the changes in kinetic energy and change in potential energy. The video displays a spring with a mass attached to it fixed at an attachment point shown here. We can assume that the mass of the spring is negligible, and therefore the kinetic energy of the spring is also negligible. Thus, the total kinetic energy is the same as the kinetic energy of the mass alone attached to the spring. At the attachment point, there is no non-zero contact force. However, this force is not responsible for the stretching of the spring, as there is no displacement at this attachment point, and thus no energy transfer by this force from the surroundings to the system, so no work is done. From Tracker, you can see that the mass oscillates and the spring moves up and down. Before analyzing the motion in Tracker, I first calibrated the motion frames using the given length of the spring at the vertical, which was 0.7 meters. The origin was set at an attachment point of the spring, so the spring hangs in a negative y direction. Once all the point mass locations were extracted, graphs of the x positions versus time and the y positions versus time could be output. From this observed motion, you can see that the spring does oscillate at about the set origin over a period of time, which I will address in more detail later in my video analysis. After gathering data from the observed motion of the system, I then constructed a computational model of the system's motion to predict the change in energy of the system and the position and time of the system. First, initial conditions were input, including the mass of the mass attached to the spring, the initial position vector of the system from Tracker, the initial velocity, which was 0 as the spring mass is released from rest, and the acceleration due to gravity. The spring constant and the relaxed length of the ball had to be calculated from information given to us in known physics concepts. Since the motion observed in Tracker displayed oscillatory motion of the spring about the origin, we can find the period of these oscillations, or amount of time it takes the spring mass to travel from the full wave to the 0 position on the x-axis. As the period is equal to 2 pi multiplied by the square root of the mass divided by the spring constant, we can solve for the spring constant k by recognizing the spring mass has periodic motion. This was determined to be 6.87 newtons per meter. Furthermore, we can also solve for the relaxed length of the spring, since we are given the length at the static equilibrium point in which the spring force is equal to the weight force. Thus, mg is equal to ks. Solving for L naught, we get 0.1265 meters. The calculation for the length of the spring is represented by these assignment statements, in which the length of the spring is calculated at each time interval over the system's motion. L hat represents the direction of the spring. As before, the value s quantifies the distance the spring is stretched or compressed and is used in the calculation of the spring force and spring potential energy. The necessary assignment statements to model the change in energy of the spring are located here. Next, we know the agents acting on the system, thus I could determine the net interactions acting on the spring and mass. The vector force due to gravity is in the negative y direction here. The force of the spring is known from Hooke's law, so the vector spring force is here. Finally, the net force is equal to the sum of these two forces. From Newton's second law, we can relate the net force to the final velocity. The net forces acting on our system change in motion, which in turn change the acceleration and thus the velocity as well. The impact of the net force on the system's motion is stated here in the calculation of new velocity values along the system's motion. Subsequently, changes in the spring and mass's position are accounted for here. Next, to update specifics of the spring, these assignment statements were included with the change in position of the spring. The extent of the stretch or compression changes as well. The changes in the calculated energies at each of the systems. After running the module, you can see the observed motion from Tracker data represented by the red ball and the predicted motion, which is the blue ball. From the plot of the predicted versus observed motion in the y direction, you can see that the computational model does a fairly good job at predicting the oscillatory motion of the system. Disparities between the predicted and observed motion could possibly be due to the exclusion of the drag force from air resistance as the spring and mass swing through the air. Also, dissipative energy was not accounted for, in which kinetic energy is transformed into thermal energy. We can also view a graph of the changes in energy versus the position of the system by running the module. Here you can see that the yellow line is the total change in energy, or the sum of the blue, the change in kinetic energy, the red, the change in spring potential energy, and the green, the change in gravitational potential energy. We can interpret the data presented even further following these discussion questions. First, it is important to recognize if the system's motion observed throughout this lab actually satisfied the energy principle. We know that the work done by the surroundings of the system is zero because the system encompasses the Earth, spring, and mass, thus there are no surroundings to do work on the system. So by the energy principle, the change in energy, which is equal to the work, is also equal to zero. As indicated by the graph of the energy versus position, you can see that the yellow line, which is the total change in energy, is constant and equal to zero throughout the motion of the spring and mass. Also, you can notice that the inverse relationship between potential energy and the kinetic energy of the spring. It is also important to recognize the slight disparity between the motion data and the x and y direction of the spring and mass's motion. The motion in both directions exhibits oscillatory behavior, however, their periods are slightly different. As you can see, there is a 0.105 second difference between the periods calculated. The mass moves left to right like a pendulum and up and down due to the spring. Thus, the period for the motion in the y direction is dependent on the length and acceleration due to gravity, and the period for the motion in the x direction is dependent on the spring constant and the mass. Thank you for watching.